So right now, we did this yesterday. We did the long way with the different lines and then looking at the slopes, what do they approach. I showed you, I kind of cheated and showed you how a derivative finds the same thing. Then I said, uh-oh, in homework they're going to say, have you identify, is it a pre-cal thing or is it a calculus thing? How on earth would we do the calculus? Did you guys find anything helpful? Let me get out of parametric mode. Sorry, this is where calculus BC is starting. Boop. Okay, and then go out. Ah, sad day, it's already there. Shh, it's not there. Huh?
Second trace.
Second trace. What's the second trace? Does anybody see anything calculus-y? Remember that from the summer packet? dy dx? We didn't talk about it much. It was in those videos at the end. Dy dx actually denotes a derivative. So if we were to put into our y equals, for instance, what's the function? Oh, x squared. Duh, I should have done that. And if we were to graph it, remember the second trace thing only works on a graph, right? With zeros and minimums and maximums. And if I was to plug in number 6, the dy dx, there's no dy dx. Oh, tell it where to go. Oh, I don't want to. Where are we trying to find it at? 1? Okay. Oh, I did 21. Go to. 21's not on my window, so it's not going to be able to find it. Hey! Did it find the same thing? We found 2 different ways yesterday. Think you can do that from the home screen too? If I can actually get to hit. What about the math menu? Anybody go there? There's an awful lot of stuff in that math menu. Go down to number 8 perhaps. What's number 8 look like? Nderive. Nderiv. Uh-oh. Okay, this is more complicated. Has to do more with notation. But ddx, if I'm using a function of or with x's, and some of you are like, no way, my calculator can do my whole homework this year, except, here's a struggle, an 83, 84 plus, none of them would be able to tell you the derivative of x squared is 2x with the power rule. Not going to happen. But they can tell you the derivative of x squared when x is equal to 1 is 2. Pretty cool. So for right now, in the preview to calculus, could you do a little bit of calculus using your calculator?
Yeah.
Hey. Okay, come back. This was all exploration number 1. Let's quickly summarize what we saw in exploration number 1. I just need to go find my slide. Here he is. Okay. With pre-cal, can we find a secant line through 2 points? Yes. With calculus, can we have the secant lines, the second point of the secant lines approach the original point and possibly make a inference as to what the slope of the tangent line is? Yes. But how? We need limits. Quickly, in your notes, give me a quick sketch of that just to be like, this is how you solve the tangent line problem. Just a quick sketch. Don't need tons of details.
You want both of them?
Yes, please. Because this also gives you a quick reminder. Pre-cal, we can find the slope of a secant line. Don't need to label all the delta x's and the crazy things like that. Let me make it a little bit bigger for you. Don't need to label all the delta x's or anything like that. Just show me a secant line and be like, oh, that's right, slope formula. Got it. Then show me the, we need a slope of a tangent line. Slope of a tangent line. And how do we do that? We could say something like, find what the slopes of the secants. Secants means secant lines are approaching. That's what we did yesterday. We looked at and it got approaching. Got closer and closer to 2. Okay, it's well approaching. Oh man, it was hard to write approaching a second ago. Is there a symbol that could just encapsulate that idea? Oh. True. We're mathematical. We like symbols and shortcuts, right? All right, so you guys are just writing down. Formula. What problem, Chris? No formula for that. Right? Okay, struggle. That's the problem. Remember, math comes out of problems. So, look at that and say, it's not a triangle, it's not a circle, it's not an ellipse. How do you find the area of an ellipse? Another day. It's not a square. It's not a trapezoid. It's not three-dimensional. We got nothing. Nah, we don't have nothing. We do have nothing. We don't have nothing. We have something! Right off top of your head, for this problem up here, for instance, I think this might be a homework problem. If I want you to find the area under this curve, kind of similar to the one up there, it's not a perfect geometric shape, you wouldn't be able to answer with like, I don't know, 3 decimal places of accuracy exactly what it is without using your calculator or calculus. But you could say something to the effect of, but I can even estimate it. How could you estimate it? For this one. How could you estimate this? You don't even necessarily have to do it in the strategic and the systematic way we're going to learn that we actually should figure out how to use. What kind of shapes could fit in here?
Circles.
Circles, maybe, like a circle leads in, maybe not a circle. What else? Triangles, maybe. We could do like one big triangle, right? Worst comes to worst, and we were going fast, wouldn't that be close? Maybe. What else could we fit in there? A rectangle? Hey, that might be better. Because a rectangle, I'm seeing this one. You guys seeing this one? Maybe-ish. And then couldn't we maybe do like a, maybe like a triangle here-ish? Something like that. And then maybe like another rectangle here-ish. Maybe a triangle here-ish. Yeah, we could do that. Close. We could do that. We could play around with stuff. And there's a place for that in homework. Does anybody know or remember? Did you go there in homework? There's a place for this. Where was it? Yeah, it was in the 1 through 10. I think it was like starting in problem 5.
Yeah.
Now, some of the shapes were perfect. Just use area formulas, easy cheesy, right? But some of the shapes were like this. You kind of have to put some shapes in there and be like, right? And the nice thing is about the graphs in the book, you can actually count the tick marks and figure out the lengths and the widths and the bases and the heights and add it together and get a number. But the problem is, wouldn't the shapes change every single time based on the figure? Well, maybe that's not a good systematic approach. So let's keep going. Group exploration part 2. We'll see how fast we can go. In your notes, we're going to do this together real quick. Then I'm going to send your groups to do an even better approximation. But it's going to be in a systematic way. So hold on, in your notes, here we go. You don't even have to write down group exploration part 2. Just in your notes, we're going to go ahead and approximate the area underneath. Hey, who's the function still? There he is. Are we still using the same portion as is on your turquoise sheet, wherever it went? Yeah. Now hold on. We want to find this area. Can we do that without using a calculator or calculus? No. Can we estimate it? Sure, you can kind of like pick a triangle-y thing, but that's not the point. We're trying to have a systematic approach, okay? So hold on, take away the triangle-y thing. We're going to use rectangles. Later on, like second semester, we'll use trapezoids for a little bit. How many rectangles, well, let's start over here. How many rectangles are being fit in? 5, right? So then if they're equally spaced, which they always are if it's given to us by the book in like one of these figures. Question, what's it been split up into? 0.2s, or you could do 1/5, but most of you would much rather work in decimals. All right, fine. Okay, so what has this one been split up into? Ooh, struggle, huh? 0.2s as well. Now, here's the idea. Even though we can't necessarily get the entire thing perfectly, what we can do is name each of these rectangles and say, hey, what's the area for the first rectangle, second rectangle? How many total? 5, right? We can find each of these shapes, rectangles specifically, separately, add them all up, and have an approximation. Now, how do we find areas of rectangles? Base times height. Now, hold on. Look at your rectangles. Specifically, in this example, how wide are the bases? 0.2. Ah. So every single one we can put 0.2? True? But is that enough for area? No. What else do we need besides the bases of 0.2 distance or length? We need the heights. But what kind of values are the heights? Heights. Josh, louder. Y values. Now hold on. Which Y values? Wait, Y values? Who are the Y values? Oh, that's right. Y values come from Y equals who? X squared. So we need to figure out what X to find the Y. Now, look at this rectangle. Struggle. Look at this one. He's the easiest to see. Am I plugging in 1 for the height or 0.8 for the height? Because it's 0.8's Y value, right? So I'm plugging in 0.8. Where? Oh, the Y. So it's going to be, for the height, 0.8 squared. Because that's the point. X, plug it in, Y. And his Y value gets me the height of the rectangle. Now go back a rectangle. What X would you use for the second, or I should say fourth rectangle to find the height? 0.6. So it could be 0.6 squared. Next one. 0.4 squared. Do we see a pattern? Next one. Uh-oh, where do we go after that? Yes. That's why you can't see him. He's not there. Now, come on, you guys are amazing. You have calculators, right? How would you put that in your calculator? The whole thing? Maybe. But couldn't you also be a smart math student and say you could factor out a 0.2 and not have to write it 5 times? Go team, right? Then couldn't you just add together each of the others? Like 0 squared plus 0.2 squared plus 0.4 squared plus 0.6 squared plus 0.8 squared. Dun, 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 dun. Get me an approximate area. Plug it in. Go. While you guys do that, I'm going to set up the next one. I'm just getting ready. What'd you guys get? 24 point, no, point, sorry, point what? 0.24. So we can area, according to this one, is approximately 0.24, or, okay, hold on. How would I set up the next one, which is, I think, is that circumscribed? It's on the outside. We could call it an upper sum if we're being super snazzy. What heights would I use for the last rectangle now? 1, because it hits at when x is 1. It's 1's y value, which would be 1 squared, right? How about the next one? Oh, that's going to be a struggle. 0.8 squared. I'm going to do this. I need to orient my board. You guys keep going. Oh, Windows 10. Make it sound like sounds from heaven. Okay, how about now? More room. Just fill in backwards. So last rectangle hits at 1. The one before hits at 0.8, 0.6, 0.4. So I'm just going to plug in. We have 0.2 squared, 0.4 squared, 0.6 squared, 0.8 squared, 1 squared. Who already plugged it in for me? What did you get? 0.44. Now, how bad is that range? Not bad. If you were measuring like inches, it'd be pretty close. But if you're measuring miles, could that be a little far apart? Okay, so we can make a deduction. What do you guys think based on this one? If this is below some air above, or above some air above?
34.
34? Okay, so our guess right now is maybe 0.34. What could make our process better in the sense of making it a closer range and a better approximation? More rectangles. So ready, in your groups, I want you guys using your spiral in the back as your work. And somebody with an expo, I want you to divide into 10. 10 rectangles. Ready, set, go. Wait, there's two different ones. Okay, group 1, inscribe. Group 2, circumscribe. Inscribe, group 3, circumscribe. Group 4, inscribe, circumscribe, inscribe. Circumscribe. There was one more group, right? Ready, set, go. You only have to do one of them. Maybe a new artist, maybe not. Depends on the calendar.
What's inscribed and circumscribed?
You're doing inscribe. All your rectangles.
And circumscribed.
Circumscribe the rectangles are over like that.
Okay. So inscribed like rectangles.
What do you label this? Why don't we just form it? Is it that? I think this one's really important. Inscribe this one below the line.
It's a 10. Inscribed is where it's underneath the lines.
So you're subdividing, an artist is drawing, people in your notes, you're calculating, right?
I'm the artist here.
What is this the? That's what I got. That's what I look like, right? So A1 is equal to 0.1. What? 0.1. The boss is up over here. Yeah, he likes you. Yeah, you can. I think that's my cousin.
This time went 0.
Oh, it is?
This time it went back.
Oh, cool. Alright, let's do this, Kyle. 0.1.
That's where it got me.
No, wait,
Sorry guys, so Shandy, pardon me. Joyce. Something about yours.
there's 10.
Amy.
0.1. We're calculating by 10.
Wait, what?
Inscribed is under, yeah.
Wait, you see?
Uh-huh.
So is this, wait, for A1, A1 for circumscribed?
Yeah.
Is there 0.1
I know how to do it.
0.1 times, remember you have to plug in the x to the function, so you have to square for this one because it's x squared.
Oh, okay.
You have to figure out if it's inscribed, you start at 0 and go 0.1, 0.2, 0.3, squared, 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 squared. If it's circumscribed, you're starting at 1 and working backwards. 1 will start at 0, 1 will start at 1.
Yeah, it has to be forward, right?
Does that kind of make sense?
Do we find the area or just graph it?
One person's graphing on your turquoise sheet, everyone else should be solving.
Okay, well now we have to solve. So we have to solve the area. The way that she did it.
What? That's the answer.
It was, oh, okay. I remember it was like, well, each thing was point one and then oh, yeah. Oh, then
I'm hoping like one more minute.
What?
I'm hoping one more minute for this.
Just do 0.1, 0.2. Because it's accounting for G.
Has anybody figured out what the bases are?
This is the height of it. This is the width.
How wide is this? If it's a tenth, 0.1. 0.1.
how many do we have?
Inscribed people, where are you starting?
Let's get the A10. What's it?
This would be point one to the 10.
No, it's gonna be 0.1 squared
Oh, yeah, if you want to.
times,
Actually, Jake is privileged, so he doesn't get this.
so, okay, so x is, yeah, so the rectangle is, x times y, right? So x is gonna be 0.1, and y is gonna be 0.1 squared.
0.5.
Then it's gonna be, 0.1.
Wait, no, we're doing cert.
0.2 squared.
Okay, so you're over.
Yeah.
That means you should end at 1.
That's gonna be
Yeah, that's why it's one.
So then we're just gonna keep doing that until we get to
until
one.
1, yeah. Then you add it.
Okay.
You see it?
Yeah.
Show him. A little bit longer for calculating.
You had to erase it all. Let's pretty nice. Right.
Which is like fine. Yeah, but
That's just this.
how do you describe the width of
There's nothing like this. I don't think.
There has to be some. You guys.
I don't think it's just a circle.
But then why is it
That's like
yeah, slope of a particular point is that line, but the line doesn't have a constant. Yeah, okay.
Are you guys making sure
It's hard to describe.
That's what this is. Can you just copy paste it from the I don't know.
Just checking real quick, inscribed people. What area did you get when you hopefully added something similar to this? 0.285?
I'm wrong.
We just.
I'm wrong. I added 1.
How about circumscribed?
What?
Now, double check calculations. Maybe something went a little funny, but that's what period 1 inscribed, circumscribed people got. Question. Where would be the middle of that? Calculate. Can't you just add the 2 and divide by 2? Just average the 2. Come on, guys. You have to find the middle.
0.335.
Nice. Huh. Before it was 0.34. This one's 0.335. 5. Remember in homework they might ask you to do something like this exactly? Because it's a calculus-y thing? Guess what you're going to do? There's a thing for this as well. Go to your graph. You have x squared, true? How do we find area under? Question, what was underneath the derivative? This weird messy thing? Yeah, the weird messy thing. Otherwise known as Joyce and/or Kindle integral. Wait, it says lower limit. That's weird. What's lower limit? Wait, where were we starting? What x value? 0. Where were we ending? What x value?
1.
It even shades it. What was the area? 0.33333333. How'd we do the second time? We get closer?
Yeah.
How would we have gotten even closer?
More
More rectangles. Do 100, do 1,000, do 1,000,000, and you're all like, no, please, Missy, no. Okay, hold on. Let's get back to notes.
Yes, it's not.
What's the idea in your notes? What's the idea? The idea with pre-cal, you can do one set area at a time, and you can find for a set area equals, you can add together a certain number, like this one would be 1, 2, 3, 4. And you can find an approximation by adding together a few areas of, say, rectangles. But how do you make it precise? How do you actually approach the actual area? You got to increase how many rectangles. And so we figure out the number of rectangles, basically, to be honest, approaches infinity. We keep on thinking, what if you were to add more and more and more and more? You get closer and closer and closer and closer to who? To what? And that's the area. Or we could say as the base approaches 0, a snazzy way of putting it, because all the rectangles will get skinnier and skinnier and skinnier and skinnier and harder to draw. People with the expos and the cool turquoise sheets, just make sure they're erased. You're going to bring it with you and just turn it all back in up to the front, throw away the napkin. But please make sure it's fully erased. Now listen. We've pretty much gotten to the end of section 1.1. But what did we really not get much into? Homework help, right? So let me give you a few hints. We're going to talk through homework questions tomorrow. And please believe me, this is a very abnormal homework. I kind of just covered first semester calculus, second semester calculus in 2 days. Okay? Now listen. When a problem says rate of change, okay? Rate equals distance over time, true? Yes. The same way distance equals rate times time. What does this look like if you would graph time and distance?
A slope, a line.
Slope. Rate is slope. Listen up carefully in homework. Do the best you can. If you come to a problem that's, you know it should be calculus, just write it down. We'll talk about it tomorrow. Do the best you can. If it's pre-cal, try the best you can as well. Bye guys. I'll see you later. See you later. Make sure to turn in my stuff on the way out. Those people who have it.